So we're looking at our normal distribution, and I want to define what a normal distribution is. I'm going to show you a few things that are related that you won't necessarily have to know the technical details, but I want you to see them. But I want to talk about what the distribution is, and then also we're going to focus on how to use it specifically. When we're talking about the distribution of data, we're talking about if we look at how often or how likely certain outcomes are to happen, what does that look like on a graph? Okay, and when we're talking about a graph, we're talking about what's known as a probability density function. Okay, we'll look at the actual equation for this in just a moment. But I want to start out by defining a certain thing, because what we're trying to measure here is the likelihood of a certain random variable, and what we use for this random variable is this capital X, okay, or uppercase X. And in the case of a normal distribution, X is continuous. That means it can be any real number, and it can be, there are no distinct values that are separated, okay? And one thing that we'll point out here is that because this is a continuous distribution, what this notation here says is the probability that a random variable x will equal a specific value of x is 0. You might say, well, then how do we find any probabilities at all? Well, we're going to find the probability of x being within a certain interval. Okay. It's going to be within a certain interval. Now, let's talk about why is the probability equal to 0. The reason is because if we're on a continuous scale, we're talking about things that can be measured. And what we're recognizing is that no matter how accurate, no matter how precise we try to measure, we can never be absolutely certain that that measurement is exact. For example, if you use a ruler that has centimeters and millimeters on it, you can kind of eyeball and approximate down to like the 1/10 of a millimeter. Or if you have a really precise caliper that you're measuring with, you might be able to get down, down to thousandths of a millimeter or something like that. You might be able to get really precise. But we recognize that no matter how precise we try to be when we're measuring, there's always going to be some point at which we have to round, or, we can't measure any more precise than that. So we would say the probability that we're on an exact value is 0, okay? Because we never know exactly if we are on that value or not. So that's why we're looking at intervals. Now, I'm going to show you what I was talking about, the probability density function. Do not bother writing down this equation, okay? I want to show it to you because I want to observe a couple of things about it, okay? For the normal distribution, this is the function we're talking about right here. 1 over sigma times the square root of 2 pi times e 2, and then this is the whole exponent. Negative 1/2 times x minus mu over sigma squared. Okay? Again, don't bother writing this down. But I want you to take a close look at that and what two things that we've already talked about are involved in that function. Sigma, which is standard deviation, and what else? It's 1 over sigma square root of 2 pi times e to the negative 1/2 x minus mu over sigma squared. Well, this whole thing ends up being squared. That's okay. Mu. What does mu stand for? Huh? The mean. Okay, remember you can use x bar or you can use mu. And if you go on and study deeper into statistics, you'll learn the differences of when to use which one. But we have sigma and we have mu, the standard deviation and the mean. Okay? Now, standard deviation is related to what other value we also looked at? The variance. The variance is the standard deviation squared. Okay? Now, I point all that out to show you this. This is notation that you need to be familiar with. When we are describing a distribution of data, we could say here that the random variable x, notice it's an uppercase x, and then we have this little curvy part here. That's called a tilde. Alright? It's on the keyboard even. X, that just means is distributed normally. That's what the N stands for. Okay? So X is distributed normally, and then in the parentheses you'll have two numbers. The first number will always be our mean, and the second number will always be the variance. Okay? So there's the description of what that notation is saying. The continuous random variable x is distributed normally with the mean and that variance that's given. So for example, if I said x is distributed, whoop, forgot my n, like that, and I said 5 and 4. What's my mean? 5. What is the standard deviation?
4.
What's the standard deviation?
2.
2. Okay? Because in the parentheses it's mean and then variance. Okay? Now, I will tell you, if you look this up online, you will find some people who do put the mean and standard deviation in the parentheses instead. Okay? Our book, the IB book, both use variance in there. Ms. Skokin, does the AP put variance in here?
No, mean and standard deviation.
Okay,
Yeah.
so AP uses standard deviation. IB puts variance in there. Okay, so since our textbook and the IB both use variance, that's what we'll use. Okay, so that's where, guys, if you're looking up stuff, just look at your context and make sure you pay attention to what that website or whatever is actually using. Okay, but we will always use variance for our purposes. Okay. All right. Let's try. Let's actually look at a couple of different distributed things of data, and then we'll actually look at the curve itself. Okay. You guys are probably familiar with, or at least some of you already indicated, you're familiar with this bell curve or the normal curve. Okay, we're going to look at how to construct one of these given certain data and actually infer some things from it. Okay, so first of all, we have this random variable A. We'll use A, B, and C for our random variables. A is distributed normally, and then what would we put in the parentheses?
25, 25.
25, 25. Okay? 25, 25. Okay? Now let's look at how we would use this to construct a normal curve. First of all, that highest point on your normal curve is always going to be at your mean. Alright, so we're going to label 25 right here on a number line. Okay, or you could call it, it's actually the x-axis. Alright, that's the mean. Okay? Then, when we sketch these, we are going to look at up to 3 standard deviations away from the mean. Now let's look at what we mean by that. Okay? If I were to take the mean and add 1 standard deviation to it, what value would I now be at? I'd be at 30. Okay? Standard deviation is 5, so 30 plus 5, or 25 plus 5 is 30. Okay? If I went another standard deviation, I would be at 35. Okay? That would be my mean plus 2 standard deviations. Okay? And then I would go another standard deviation, the mean plus 3 standard deviations. And I would end up at 40. Okay? Now, what's going to happen here is this is going to give me half of my bell curve, my normal curve. It's going to start going down a little bit by the time we reach that first standard deviation. It's going to go down a little bit more by the time we reach this second standard deviation. And then it's going to be actually pretty low by the time we reach our third standard deviation. Okay? And I can use this now to draw the right-hand side of my normal curve. Any questions so far? Notice 2 things. Number 1, this continues forever. Remember, this function is defined for all real numbers. Okay? Another thing to recognize is that it will never hit the x-axis. Okay? So that x-axis is actually an asymptote, okay? X will never equal 0. Now, question, what's the probability that my value equals 30? That a random variable equals 30? Oh, we said this one of the first things. 0, okay? What's the probability of us actually hitting any one value exactly? It's 0, right? What we're going to use this normal curve for is to find probabilities of ranges. For example, we're going to be able to use this to find the probability that a random variable will be between 30 and 35, or greater than 30. Okay? But we need the left-hand side here as well. So what we're going to do on the left-hand side is we're going to subtract 1, 2, and 3 standard deviations. So we have the mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. Okay? So we have, what value would this be? 20. And then this would be 15, and this would be 10. Okay? Now, our bell curve should be symmetric. So I put this this high, so I should end up being at about the same height on the left-hand side. Okay? At 35 it was this high, so at 15 I should be about the same height. Okay? Now I'm not going to get a ruler out and measure, but it should be pretty close. Okay? So we have this symmetry, with our mean being at the highest point, and then we have 1, 2, and 3 standard deviations away on either side. Okay? Does that make sense?
Yeah.
Alright. Now we can do this with all 3 of these different distributions. Okay? We'll do it again with B here, and then I'll just show you what C ends up being. Okay? B, we would say, is distributed normally. What goes in the parentheses? 30 and 4. Okay. While we're here, by the way, C would be distributed normally. And what would go in the parentheses? 21 and 100. Okay. Now, question. Which of these 3 is going to be spread out more? C. Okay? The standard deviation of 10, our data is spread out a lot. Which one's going to be spread out the least? B. Okay? And actually, let's see how that works. Okay? My mean is at 30. So I'm going to put the highest point here at 30. And then 1, 2, and 3 standard deviations are all going to be right in that range right there. 30, 32, 34, and 36, right? So here's 32, 34, and 36. Here's half of our bell curve. Okay, for B. If we go to the left, we have 28, 26, and 24. Alright, so you see here how it's much more crammed together. Okay? So 2 different sets of data. We could now compare these, if we wanted to, by looking at the curves. Okay. Well, let's look at all 3 curves. Here's all 3 curves. Here is the one where our mean was 25, the first one that we did. Okay, that's A. And then here's B, the one that we just did. And then here is C. Let me change these because we did A in red and we did C was in blue up there. Okay? So notice all these. All right? What effect does the standard deviation have on the curve? Alexi?
The bigger the standard deviation, the wider the curve is going to be.
Exactly. Okay? The bigger the standard deviation, the wider the curve is going to be. Now, the reason why this is significant is because we're talking about intervals of data. And like we said, the probability of one specific value is 0. However, we can find probabilities of ranges of data. And here are probabilities as given in our text. Okay? You may see other sources that have slight differences in the decimal points. Okay? For our purposes, this is as precise as we need to get. Okay? You might see 99.75 or, 67.91 or something like that for our purposes, these are the percentages that you should know. Okay? So let's look at how we would use this. Notice mean plus or minus 1 standard deviation is 68%. So that means for our variable A up there, we have a 68% chance that if we pick a random piece of data from that distribution, it's going to fall between 20 and 30 because that's 1 standard deviation on either side of the mean. Okay? That's what this means right here. The probability of picking a value between 20 and 30 is 68%.
How do you find those percentages?
Those are found using that ugly function I showed you at the beginning and actually integrals. Okay? So, yeah. If you do SL, we'll look more specifically at that, and I'm sure AP Stats, they look at that as well. But, so, we are going to look at how to use our calculators to find different intervals that don't fall exactly on the standard deviations. Okay, it's actually really cool. Our calculators are pretty powerful with that. So, now, with this being said, if that's 68%, what percent of the data is between 25 and 30?
34.
What?
34%.
34%. Because our bell curve is symmetrical, yeah. So, of that 68%, it's going to be 34 and 34. Okay? Now, the mean out to 2 standard deviations is 95%. So, the probability that A is going to be between 15 and 35 is 95%. Okay? So, let's think about this. What's the probability, if the probability of all of this is 95%, as you see here, what's the probability that a randomly picked number will be between 25 and 35? What?
47.5.
Yeah, 47.5. Half of the 95% is going to be in this range. Okay? That's 47.5%. Okay? You guys get any idea with this?
Yeah.
Now, one last thing. If this is 34% and this is 47.5%, then how much of the data is between 30 and 35? Subtract them. 47.5 minus 34, we've got 13.5% in that range. So you can see how the problem solving can come in with these. All right? All right. Have a great day. We'll see you tomorrow. Remember, tomorrow's a normal 7-period day. So, have a great day.
Thank you, sir.
You're welcome.
Isn't this like the empirical rule or something? It's similar. It's like
Empirical
I
rule.
don't know. It's something similar. It's like any bell curve is split. It's like 34, 34, and then like 17 or something. Or
You know,
something like that.
I don't know that I've heard that term, but I mean, there's all kinds of terms they could use for
We
it.
talked about it in biology briefly, so it just looked
Oh,
familiar
did you?
enough.
Okay.
Yeah.
They may use the term in biology or something. I'm just not familiar with it. See ya.
I might be like 10 minutes late after school because I have a schedule.
You heard it too?
I'll be
Fine.
Uh,
Yeah, today is my 4th reading.
See ya.
I wonder
Oh.
how we decided to hide them.
You just kind of guess. If we wanted to, we could
Have a
use
good
the
day, Mr.
calculators. You too. And that function I showed you at the beginning,
Oh,
That's, to get the exact, we would have to use that. So we're not gonna do that.
We just like for.
We just kind of approximate
No?
it.
Thank you.
Good question though.
I'm not gonna be here next Friday. So we're good.
Do I know what we're doing? We're working on chapter 2 of the new book.
Not this Friday.
Yeah.